me anything you want from the Peter's lectures, even from yesterday. So yeah, with this said, let's just go ahead and start. He puts a little revision for you guys here. So question number 1, he says in the independent samples t-test, remember independent means that there's a person in one group and another person, completely different person in another group. So A is not correct. Each person acts as their own control. This would be the dependent samples t-test. B, there are different participants in the two treatment groups. That sounds nice. The same participants in the two treatment groups. This is again dependent samples t-test. So the answer should be B. Yeah, all of you are saying B. So question number 2. This is just theory. P-value is calculated in a test by dividing the difference in means by what? Is it the population standard deviation, the sample standard deviation, or standard error? Which one do you guys think it is? Remember, we said that the T is the same as the Z value. It's the same. It's just equal to the difference in means. It was like D something minus whatever the other variable is, and then here it's SEM, right? It wasn't exactly SEM. It was standard deviation divided by square root n, which is basically SEM. So the answer here should be standard error. And I see all of you putting C. Okay, and question number 3. So the null hypothesis tested by an independent sample t-test is that the two population means are identical, the sample means are identical, or the population variances are identical. Now, first off, population variance has nothing to do with this. Now, your sample means, you might think, why is it not B? The truth is, if you take any two samples from a population, just by sheer luck, there's no way their means are going to be equal. So, just by logic, B can't be the correct answer. The truth is, a null hypothesis, like let's say, for example, yesterday's example, where I take a sample and I give them water. The null hypothesis is that the population of people that drink water should be exactly the same as the population of people that don't drink water, even though my sample is just a sample, but they represent the population of people who drink water. So the answer here should be A. And let's say you don't even know that fact, you can still think of it logically. If you take a sample, regardless of, if, like, let's say it's the same population, a population of people that don't drink water, for example. If you take one sample and another sample, just by luck, you're probably not going to have the exact same mean. So that's not really what the null hypothesis is saying. The null hypothesis means that the population means are identical, meaning that there's no difference between those two populations. Not that there's no difference between the samples. There could be a slight difference between the samples, but it's still not significant. So in 3, the answer is A. The advantage of before-after effects. Now remember that, order effects, this is a disadvantage, right? We don't like, what about dependent samples? What do you mean by, do you mean question 4, or what do you mean, Osama? Which question do you mean? Question 3. Yeah, even dependent samples. With dependent samples, technically, like let's say I gave a person, like let's say here's one of the very common ways people make dependent samples testing. So you don't give them a medication, you collect data, then you give them a medication, then collect data. So you're essentially checking the same person. First time he did not have a medication, next time he did have a medication. So you have two pieces of two groups, but he's the same person. So the first time, basically, yeah, this is the same as before and after. So the first time, he represented the population of all the people who don't take the medication. The second time, even though he's the same person, he's now representing the population of people who do take the medication. So it's the same thing. The null hypothesis, its exact definition is that both populations are exactly identical. They have the same mean, and there should be no difference between those populations. So now let's focus on question 4. The advantage of before and after effects. So, order effects are a disadvantage. There's not really an advantage. The variability between participants is removed from the analysis. Remember this? I was actually talking about this yesterday. I was saying that there is essentially, the variability from the same person taking the medication and then the next medication, it's non-existent. So this looks like a good answer. And then C, which tries to trick you, it says there's homogeneity of variances. And although you can say, okay, yeah, the same variance here is the same variance here because it's the same person. No, there is no variance to begin with because it's the same person. You don't say, oh, there is a variance, but it's the same person. No, you remove variance to begin with. So the answer here should be B, right? It's B and then C and then A and then B. So this is just a little revision. Now we're starting with ANOVA. Now, before I show you the slides, because I admit it can look a little confusing. I think the best way is to switch to the uh, to the whiteboard that I keep drawing on. So let's do that, and then share screen, and then pick that, and there you go. So ANOVA is really simple. Basically, remember how when we have two groups, we were doing the t-test and everything, we have only two groups. One group is this, one group is that, one group is, for example, taking the medication, one group is placebo, one group has their phones turned on their head, the other group has their phones turned off. It's always two groups. You never have more than two groups. So some study designs require more than two groups. What do you do then? You do ANOVA. ANOVA allows you to compare look, although it's called the analysis of variance, it allows you to compare the means of three or more groups. You can even compare the means of two groups, but it's not ideal. Essentially, you only use it when you have three or more groups. So I'm going to show you how ANOVA works right now. We're going to take two examples. The first example is going to be three groups, and basically what I'm going to check is how long each one sleeps. So, for example, this is our second group, and this is our third group. Now, for every group, I need to give them a sort of intervention or something that makes them distinct from each other. So this group will take Nova water, Nova, right? The brand, and this group will take Aquafina, right? This group will take Aquafina. Let me see the chat. Oh, I can't see the chat. I'm sorry. So this is mostly used with more than two groups. Yeah. So yeah, you use ANOVA when you have more than two groups. If you have two groups, technically ANOVA should still work fine. But if you have two groups, it's for example, when you have a problem in your body, you don't just go to a family medicine doctor and khalas, you're happy. If it's very complicated, you're more likely to get a better solution if you go to a specialist. So this is the exact same way. ANOVA can be good for two groups, but ideally you want to maximize its efficiency. You have to use it with three or more groups, or more than two groups. Same thing. When it's two groups, you use a t-test. T-test is more specialized with two groups than if you use, for example, ANOVA. So just as a very simple rule that you should always follow: three or more groups, ANOVA. Two groups, usually use t-tests. And there's a lot more tests, but just for the time being, these are the main ones that you need to know: t-test and versus ANOVA. So let's keep continuing with this example. So these guys will take Aquafina, and then these guys will take, I don't know, Variance. Okay, Variance. So these guys will take Variance, right? So then what I'm going to do is I'm going to analyze which water could possibly make them stay up longer or stay up less. That's my hypothesis. So my hypothesis is that one of the waters will make them, or possibly one of the waters will increase or decrease sleeping time significantly. The null hypothesis is that none of the waters increase or decrease, none of the waters have any effects, right? That's the null hypothesis. And my research question, although you don't need to know what research question is, my research question is, can one of the waters increase or decrease sleeping time significantly? So let's say in each group we have 5 people, okay? In each group we have 5 people. So let's look at the results. Now, everyone, the average for sleeping is 8 hours. So I'm going to consider that as my null value. I'm going to set that as 0. If he sleeps 9 hours, I'll consider that +1. If he sleeps 7 hours, I'll consider that -1, so on and so forth. So let's say the first guy, he slept an extra hour, so he got +1. The other guy, he slept an extra 2 hours, okay, he got 2. The third guy, he slept 8 hours, so he's 0. Fourth guy, let's say 2, and the last guy, for example, is -1, okay? He slept 7 hours. Then these guys, for example, he slept 2, he slept 1, he got 1. These guys are -1, and then another, for example, -1. Okay? And then let's say again, none of the water brands have any effect on sleeping time. Yeah, I'll give you the reality. The reality is that none of the waters affect sleeping time, but we don't know the reality. I'm trying to find out using ANOVA. So this is how ANOVA works. I'm collecting data right now. So now I went to the last group. So he got a 1. This guy got a -1. This guy got a 0. This guy got a 2. and this guy got a 3, right? Okay, so now on the surface, without even doing any calculations, it already looks like none of the waters are affecting sleeping time. It looks like they're all regular, right? So how would ANOVA work? First off, ANOVA does two things. There are two very important things when it comes to ANOVA. Something called between the group variance, which basically analyzes the variance between the groups. So how does the variance in this group differ from this group? How does the variance from this group differ from this group? And then there's something called within the group variance. So for example, notice how even though these guys are all taking the same water, sometimes there's variance between them. And variance could be due to a number of reasons, namely two that we're really going to talk about. One is just measurement issues. So for like blood pressure, for example, here we're measuring sleeping time. So maybe like they slept 8 hours, but like 8.5 hours, but we marked it as 9. Oh, that's a mistake, you know. So sometimes you can have incorrect measurements. The other, possibility is that people are different. You know, some people sleep longer, some people sleep less. That's everyone's different. Sometimes even people are different in terms of their genes, and this can cause, drugs to work differently. So, people that are taking the same drug, they don't have to have the exact same result because people are different. That's something very common it's something very obvious for you to understand. So, this is called the within the group variance, right? And this is called within the group variance again, and this is called within the group variance. Between the groups, this is called between the group variance. Now, how do you find the between the group variance? Basically, we find the mean. So here we find the mean. Let's say the mean was, I don't know, 0. Okay, it doesn't matter, 0. And then here the mean was like 0.5. It doesn't matter too much. And then here the mean was like 0.2. Okay, so we found the means of all these three groups, and here are the means. You can notice that all these three values are very close to each other, right? Now, what does this idea suggest? It suggests that, hey, the variance here is minimal, the variance here is minimal, and the variance here is minimal. And even when you go between the groups, the variance is still minimal. That means that even if we switch treatments, nothing's happening, right? Okay, so this idea needs to really be important in your mind. That here I can without any calculations, I am sure that all of you can agree with me that if we actually did do analysis on these and calculated everything, it would end up being not significant. None of the waters, blah 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 blah. We would accept the null hypothesis, and that would be true because I told you at the beginning of the reality is that it's true. Yeah, Faris. I'll repeat, but the example is still not over. I'll repeat, but the example is still not over. There's still a second part to it. So for now, just understand this. Understand that, hey, there's no variance here. There's no variance here. There's no variance here. And even when you compare between the groups, there's no variance. So the way we understand that is that, hey, between, within the groups, nothing's happening. And between the groups, nothing's happening. So, this gives us an idea that when you go from one group to the other, when you go from Nova to Aquafina to Bahrain, there's still no difference. So this gives us an idea that the waters don't do anything, right? Because the only difference between the guys taking Nova and the guys taking Aquafina is pretty much the water, right? So just keep that in your head for a second. Let's take a second example, and I'll make this one a bit more obvious. So we concluded that water doesn't work, yada, 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 and we thought that, hey, none of the waters did anything. So now we're doing a second experiment. Now I have three groups. The first group, they will take Nova, and it's the same experiment. I'm checking, I'm checking sleeping time, yada, yada, yada. The second group is taking tea. Whoops, sorry. Second group's taking tea. The last group is taking coffee, okay? So the first group, here's what they got. They got -1, he got 1, he got 0, he got 2, and then -1. Then we calculated their mean. It became like, I don't know, 0.2. Okay? The guys with T, they stayed up a bit longer. They stayed up, for example, oh, he got a 3, this guy got a 5, this guy got a 6, this guy got a 4, and this guy got a 7. So we calculated their mean. And then when we found out their mean, let's say they got a mean of 5. The guys with coffee, one guy stayed up like 9 extra hours. One guy stayed up like 8 extra hours. One guy stayed 10 hours. Another guy was like 7. And another guy was like 10. Then we found the mean, and let's say just for simplicity, it was 9. Now notice, if we look at the variance here, it is similar, within the group. Like, let's say the variance within the group. Notice how the numbers are very close to each other. -1, 1, 0, 2. These all these five numbers are very close to each other. So the variance would be low. It will be something like 1, meaning that the variance, the distribution is very, very narrow. The distribution is very narrow. This is within the group, right? When we go to the other group, T, the numbers are still very close to each other. Let me just fix that. Let me say this was 7, okay? Because 3 and 7 are very far. So look, 7, 5, 6, 4, 7, they're all very close to each other. So within the group, variance is still very low. Still very low, right? If you draw the distribution, all the numbers are close to each other and cramped to each other. It's not like he's getting 0, then 10, then -10, then 10, then... No, all the numbers are close to each other, similar to the Nova water. So the variance here is also 1. With coffee, even though the numbers are big, like 9, 8, 10, 7, they're all close to each other. 9 is very close to 8, very close to 10, very close to 7. So also within the group variance, if you draw the distribution, it's very narrow. And this will be also like 1 or maybe 2. Like, the idea is that when you look at each group, within the variance is very small. But now, when you compare between the groups, you look and say, holy, what the hell? The means are very different. There is a very big variance between the groups in terms of their means. That's what between the group variance means. It doesn't mean we're analyzing the variance between the groups. It means we're looking at the means between the groups. And is there a lot of variance between them or little variance between them? Here, there's a lot of variance. Look at how here they have almost a mean of 0.2. Here they have a mean of 5, and here they have a mean of 9. So if we did analysis here, it would tell us there is significance. And it makes sense. Look, here they're not sleeping that much. Here they're sleeping an extra like around 5 hours. Here they're sleeping an extra almost 10 hours. So here, between the group variance is high. And this is telling us that the treatments are actually making a difference. Compared to the previous example, where between the group variance wasn't really making that much of a difference. They were all close to each other. So the treatments weren't making a difference. Okay. Do you all just understand this idea so far? Forget within the group variance, just between the group variance. Do you all understand that when you have a really high between the group variance, where's the chat? Okay, I'm seeing guesses. It makes sense, right? The only thing that makes a difference between each treatment, between each group, is the treatment. So if you see a big difference between each group, then that means that the treatments are working. So now, why did they talk about within the group variance? Okay, so I'll tell you why. It's because examples are not going to be as obvious as this. They're not going to be -1, 1, 0, 2, -1. They're not going to be very simple. You see, let me give you a difficult example. So let's use the same exact example, but I'll change the numbers to make it more confusing. So let's do Nova, and then we have T, and then we have coffee, okay? And let's, for the sake of it, the reality is that coffee is significant, tea is significant, and Nova is not significant. It's the same as the regular population, all of them compared to the regular population. So look, with Nova, let's say they get 2, 4, 0, -2, and then 3. And let's say with T, they get 7, 8, 4, 3, 2. And then with coffee, they get, for example, 10, 11, 5, 6, and then 9. Now, here is where the problem happens. How do you know if it's the treatment making the difference or if it's the individual person? So maybe if this guy took coffee, he would get like a 12, but you're giving him tea and instead he got a 7. So how do you know that this person is very different from this person, or if it's, for example, or if they're the same? That's where within the group variance comes into play. Basically, I'll get to the questions. Just relax for a minute. Just listen to what I'm saying. If the within the group variance is big, then you have to take caution, because like if let's say here, for example, the variance here in between these numbers is 5, then you can't really say that, oh, coffee is the one making the difference, because you know their marks are all over the place, similar to how coffee's marks are all over the place, similar to how tea is all over the place. The idea is that when you look at within the group variance, if it's the one being big, then maybe it's not the treatments doing the thing. Maybe it's the people being different that's doing the thing. Maybe it wasn't coffee that made him sleep an extra 10 hours. Maybe it's just because he's different. And he, like, let's say coffee didn't do anything. Maybe he just alone slept an extra 10 hours. It's possible. Now, how do we remedy this? We calculate. We form an equation. Now, what's this equation? It's very simple. Between the group variance over within the group variance. If this overall number was high, it means that this number dominated the bottom number. It means that between the groups, there's a lot more variance going on than within the groups, and they're all differences and so on and so forth. That means treatments are working. That means we're getting closer to significance. That means we're getting closer to the p-value being less than 5%. That means we're getting closer to the confidence intervals not intersecting the means, blah, 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 blah. Significance. However, if this number was low, it means that the within the group variance is what's causing the changes. It's what causing the 2 and the 10 to appear, not the treatments. It's the within the group variance that's causing all these different numbers and everything like that. So if the within the group variance dominates the between the group variance, the overall number will be low, therefore suggesting no significance. Does everyone understand this formula? Before any questions, does everyone understand this formula? Yes. This is ANOVA. Okay, you guys, I saw a no. It's fine. We're going to keep repeating this. It's fine. So, yes. Okay. So look. Did you guys understand this first example where there was no variance between the groups, and then there was no variance within the groups? So we said that ultimately what would happen is between the group variance over within the group variance, both numbers are low, you would get an answer close to 1. If you put 1, this is called an F value, right? We have Z value, T value, now F value. If you put this 1 into an Excel sheet to get a P value, it would tell you it's not significant. It would give you a number more than 5%, so no significance. In this second example, it's different. In this second example, the between the group variance was large, and you don't even need to use calculations. You can just look, everyone's getting here a number close to 0. People are getting numbers close to 5 here, and people are getting numbers close to 10 here. It already looks very obvious that tea and coffee are having an effect. So let's say we calculate. You'll do between the group variance, it will be high. You'll do within the group variance, it will be low. So you'll get a very high number. Let's say you get, for example, 5. If you put 5 into the Excel sheet, it will give you a p-value, maybe like 0.005, 0.005. So like, 0.5%, which is significant, very significant, right? So here it would tell you that there is significance, okay? And that coffee and tea and blah, 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 they're doing something. Okay. Here in this example, it's slightly twisted. The within the group variance is high, and the between the group variance is high. But the question is, which number is dominating the other number? So let's say the between the group variance, let's say it was, for example, we calculated it, it was 8. And the within the group variance was, for example, 4. Let's say we put this into the Excel sheet. I'm just making this number up. We got an F value of 2. You put it into the Excel sheet. The Excel sheet will tell you, hey, we got a p-value less than 5%. It's significant. I just made this number up. I don't know if this will become significant or not. But the idea, the entire idea of ANOVA is that if we have, for example, 3 groups, you will check within the group variance of each one. You'll calculate it. okay? And then you'll have a grand within the group variance. Then you'll check between the groups by checking their means, and you'll calculate that. You'll put them on top of each other, so between the group variance over within the group variance, and then you put equal, and you'll get a value. If this value was high, it means that between the groups, that's what caused the difference. Now, what's the only difference between the groups? The treatment. This person was taking Nova water, this person was taking whatever tea, this person was taking coffee. The only difference between the groups is really the treatments, right? It could also be individual differences, but the main difference is the treatments. Within the group variance, it's all about the people's different the people's differences from each other, as well as the inaccurate measurements. So if the between the group variance was high, it would dominate. You'd get a high number. It would push you to a p-value less than 5% significance. If the within the group variance was high, it would dominate. You'd get a very low number, under, for example, 1. You'd get a p-value of, for example, greater than 5%, like 20%. You would say there's no significance, and that the confidence intervals will not touch the means, yada, 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 all that stuff that we talked about yesterday. Is this clear with everyone? This is how ANOVA works in a nutshell, but I'll show you how they calculate everything as soon as I can get the chat up. Where the hell is the chat? I'm gonna have to stop the share. Okay, so you're all saying yes. I'm happy that you're all saying yes. Is there anyone that doesn't understand this so far? Can you please repeat? Yes, I will repeat. I will repeat as many times as you wish. Where is the PowerPoint? Okay, put this here. So I will repeat. So we do the equation for every criteria. You look there. You do the equation every single time, right? For any single study. Like I will give you another example now. Okay, so let's do an example right now. But I'm not gonna waste too much time on the numbers and everything. I'm just gonna give. Okay, let's just do this. Let's just do this. So here's the example we're gonna do. Let's say we're gonna use the same example. Okay, so is there a better example? Okay, satisfaction levels with actually no, this is just pain level. That's a lot better. So no treatments. Let's say our first group is no treatments. Our other group is NSAIDs, right? We give them NSAIDs. Yeah, so you need to calculate variance always. Yes, you do. So here's our second example. So NSAIDs. We took all the cancer patients, and the last group is morphine. Okay, now what's the reality? No treatment will keep their pain. NSAIDs will reduce their pain slightly, but significantly. And morphine will reduce their pain significantly, but by a very, very larger effect size. So morphine does the big magic. But now, how do we use ANOVA? How do we use ANOVA? So let's say this guy got, for example, his pain didn't change. This guy's pain increased because he's different. He could have his pain increase. This guy's pain is the same. Okay. So the variance within this group is very low, right? 0, 1, 0. All these numbers are very close to each other. So the variance within the group, we calculated it. It's like 1. Okay, whatever. It's just a random number. And with NSAIDs, let's say, for example, they decreased by -3, -4, and then -5s. Okay. With morphine, they decreased by -10, -11, and -12. Notice how all these numbers are very close to each other. 0, 1, 0 are very close to each other. -3, -4, -5 are very close to each other. -10, -11, -12 are very close to each other. Now, what we need to do now is find the means of each different group. So this mean, for example, let's say 0.5. It's like 0.3 or something. This is like -4. This is like -11, right? So now, within the groups, there's not really much variance going on. Within the groups, all the variance is sort of similar, right? If you go into each single group and check the variance inside them, there's not that much going on, right? 0, 1, 0, all that same. -3, -4, -5, all that same. -10, -11, they're all sort of very close to each other. So within the groups, there's not really that much going on in terms of them being different from each other, right? There are slight differences, not really that much going on. But between the groups, oh, hey, look, we have a lot of difference, a lot. Look at this, -4, -11, yada, yada, yada. Lots of variance going on. So just by looking, no calculations, no nothing, it already looks like NSAIDs make a difference. Just because the only difference between these guys and these guys is the treatment, right? Notice how the variance is still there, but it's not causing this huge change of 0 to -3. That's not going to happen just by variance, by people being different, right? The more likely thing is that NSAIDs is doing it. And same thing with morphine. Okay, maybe if you put this guy here, he will still be -10 here. Maybe it's possible, but it's very unlikely. And that's why I'm just telling you that within the group variance for this example is very low within each single group. We found the global, or the grand within within the group variance, and we found it's like 1. We found between the group variance, and it was like 8. So now we do our formula. 8 over 1 equals 8. You put 8 into the Excel sheet, you'll get like 0.0000000000001. That means it was really significant, really significant. Okay. So before we go to all the questions, do you all understand this example? Do you all understand how we found significance with ANOVA? Yes. Okay, yes. Just the formula. Yeah. So look, we'll talk about how you calculate. We'll talk about what the formula means, why they set it up and everything. But the most important thing is that you understand the concept of ANOVA. It's that we check the variance within the groups versus the variance between the groups. Which one dominates more? Which one is a higher number? That dictates to us the p-value and the significance level, or the significance, if it's significant or not significant. So is there an ideal number we want after dividing the between and the within? So yeah, there is a specific number. I don't remember it, right? You don't have to know it. So I memorized this. Well, I was in Excel sheet and I was plugging in random numbers, trying to look for the p-value when it becomes 0.05. And the number I remember is 2.33. So if this value here at the end was 2.34, it will be significant. If it was 2.32, it would not be significant. But that's the number I remember. I don't know. I don't think that's the number right now, but that's the general idea. Okay. So, so we do the equation for every case. Yeah, you do the equation for every single study. So we need to calculate variance always. Yes, you need to calculate variance always. When plugging within each group into the formula, do we get the mean of all the groups? I'll show you how to, do not jump to calculations. I'll show you how you calculate. It's actually much more complicated, but I'm just giving you the concept of ANOVA. Like if a group had within the variance of 0.1, group 2 had 0.2, and group 3 0. Yeah, I'll show you. It's similar to that. It's not exactly like that. It's similar to that. You take a mean of them basically. But yeah, you're on the right track. I'll show you the formula. I just want you to know the concepts. So within the variance low is good. Look, Osama, it depends. Maybe you don't want significance, like the example I mentioned, where you want to prove that placebo is the same as conventional therapy. Sometimes you don't want significance. So having within the group variance dominate versus between the group variance, that will be good for that study. So it depends on the purpose of the study. It depends. Are you looking for significance or are you looking for it to be not significant? Okay. Put negative values. What are you saying? Okay, just a small doubt. When you put negative values, what did those negative values mean? So what I meant with those negative values is, for example, everyone sleeps 8 hours. If he slept 7 hours, I don't write 7, I write 0, I write -1. So for example, if I wrote 9, that means that person slept, what's 9 plus 8? 17. That person slept 17 hours. He slept an extra 17 hours, which kind of doesn't make sense now that I think about it, because this was supposed to be coffee. Right, coffee makes you stay up. So the example doesn't really make that much sense. I just recognized it, but you get the idea. Like, it doesn't matter what the idea is supposed to be. It's just that I just want you to understand that we have two main values that we're working with between the group variance and within the group variance. Based on which one dominates and the value you get at the end, you put it into the Excel sheet, and the Excel sheet will tell you whether it's significant or not. So I hope you. So which within do we choose, and when do we do the equation? When we do the equation, I'll show you when you do the equation. Okay, I'll show you everything. I just want you all to understand this simple example right now. Okay, so I was expecting we'd be very done by this part by now. Within the group variance is for every single group. Yes, I'll show you the calculation side of it. But right now, I just want you to understand the simple concepts. So let's keep all this, just in case I need to go back to it. Okay. You guys really love jumping ahead for some reason. I don't know why. Every time, like. So now, yeah, it's really important to know how to calculate because you'll probably get a question on it. Right, so this is the lecture. This is the first slide. This is actually the second slide. Let me just bring the chat up. I really recommend not jumping ahead of what, like, don't jump ahead, because like I want to answer any questions at the end. So I'd rather not like waste time on it. Okay, so this thing with the chat keeps on happening. 1 second. Okay, share this and then bring the chat up. Okay, so do you mind if let's play Maghrib and move to the slides? Khalid, if you don't mind, let's play Maghrib and move to the slides. Okay, let's play Maghrib. Okay, you guys. Where's the growth and development person?
I'm here.
6:30.
Yeah. Oh, when was Harun originally
Hello.
supposed to
Oh
start?
right, I muted. Sorry. Yeah,
Yeah, when was Harun supposed to start?
I think 6.
Oh, it's because
It's
I'm afraid that if we don't pray now, we might miss it. But that's why I suggested this.
no. It's fine. We can pray, but can we just start 6:30? Because I did not anticipate that this would take
Yeah,
like an hour.
yeah,
Okay,
no
so
problem.
we'll continue at 6:30, inshallah, maximum. So let's go pray. We'll come back. 5:45.
Yeah, I think.
5:45.
Yeah.
Okay. All right. It's 5:45. Let's not waste a single minute because we can finish this, okay? So what is ANOVA? They mentioned everything here. It's a way to test the differences between the means by analyzing within and between the group variance. And you can use any number of means, but we'll see later that it's actually better to have less groups than, like, it's better to have, for example, 3, 4, even maybe 5 groups than, for example, 20 different groups. And we'll talk more about that. I hope you're all here. Are you guys here? Yes, okay. So look, this is an example. They're telling you here that we have 3 different populations, right? And they just want to see if you can understand what the null hypothesis here would be. The null hypothesis is that all the population means are the same, all 3 of them. The alternate hypothesis is that at least one of the population means is different from the other. Okay, and it could be different in terms of positively or negatively. It could go to the right, to the left, so on and so forth. But the idea is that they don't equal each other, right? And it should be at least one. So, like I mentioned earlier, the only real things that makes within the groups different are individual differences and the errors in measurement, for example, inaccuracies. Now, between the group variance, although it's really the treatment that makes the difference, it also is subject to some variability. So individual differences still have an effect. Errors of measurement still have an effect. But our question is, do treatment effects cause a substantial difference? Because look, notice, if let's say the treatment does not do anything. Let's say the treatment does not do anything. Okay? Then this and this are exactly equal. They're almost exactly correlated with each other. They're equal. And for that reason, neither number dominates each other. You'll have a final value close to 1, and that won't be significant, right? You have to reach at least like more than 2 to get significance. So did you get this? Can you appreciate the connection? Did you guys understand this? Because this is really important. Because he mentions it here. If there are no treatment effects, then within the group variability will be the same as between the group variability. And it makes sense. If you get rid of this little thing, then these two are the exact same, right? But if you had treatment effects and if they were making a substantial difference, then this number might be much higher or even much, not really much lower, but it will be high and it'll dominate this number. Okay? Because remember, variability being high doesn't mean that the numbers are high. It could be that the numbers are low, but that would still be considered as high variability, right? So high variability could go either way, high numbers and or low numbers, right? It just means that the group is very different from the other group. It could be very different in terms of high numbers or different in terms of low numbers. But the idea is that if the treatments were working, yeah, by treatment effects we meant treatment doesn't do anything. Yeah, by treatment effects, the null hypothesis means that treatment effects here do not do anything. They don't do anything. Which makes sense. If they don't do anything, these numbers will be very close to each other. They'll be almost equal. When you put them on top of each other, they're going to get you a number close to 1. 1 doesn't do anything. If you put f value into as 1, it'll give you a p-value greater than 5%. Okay, it's a rule. So this is really important. So this is the notation I was writing before b v and then wv. That was just to not really confuse you. But this is the actual notation: s squared within. Now, where do we see s squared before? We saw it in the midterm lecture. S squared just means variance, but we have two different variants. We have one that's within the group, so you give a subscript of w. The other one is between the groups, so you give a subscript of b, right? Now, the within the group variance, it doesn't matter if the treatment works or treatment doesn't work. So it is independent of h0 being true, which makes sense. Notice this and this. People can be different. If the treatment doesn't work, people will still be different. So they will still be within the group variance. It will still be the same number, even if the treatment works or doesn't work, because that's just people are different. It has nothing to do with the medication or treatment or intervention or whatever. But between the group variance is affected by the reality. Does the drug actually cause a difference? If it does, it's going to change your between the group variance. If this exists, it will change this. If this does not exist, or if this doesn't do anything, then your between the group variance will change. It'll be low. So this is really important. This is theory. He'll give you a question telling you, for example, that the between the group variance is independent of the null hypothesis. This is wrong, right? The between the group variance depends on whether the alternate or the null hypothesis is true. Based on which one is true, between the group variance could either be high or could be low. So does this really make sense to all of you? This really needs to be like embedded in all of your skulls, because this is pure theory and he'll give you a question on it. Okay. If they are similar, you guys say no. Okay, so look. Here, the only thing that we're adding so far is that we have two things called between the group variance and within the group variance. Now, forget between or within. Any variance could be a specific number due to individual differences and errors of measurement. This is regardless of whether it's between the group or within the group. Regardless of which variance it is, that variance could exist because people are different or because there are inaccuracies in measurements. Do you understand this part so far? Okay. What should I said? No? Okay. Now, I might enter the SAT and I get an 8. Tomorrow you enter and you get a 9. Tomorrow someone else enters and gets a 7. Tomorrow someone else enters and gets an 8. Why are we getting different results? Why don't we all get the same results? Because people are different. People have different capacities of learning. People have different genes. People have different everything. So any variability that you have inside your study is subject to an increase simply due to individual differences or inaccuracies in measurements. This goes for both between the group variance and within the group variance, because they are both variants. You can never say that the variance is 100% because of the treatment, because people are different. Someone's going to take the treatment and get an 8. Someone's going to take the treatment and get a 9. How can you explain that? The only way you can explain that are inaccuracies in measurement or individual differences, or even a combination of the two. So does this so far just make sense? Any variance could just, be different because of people being different. Variance exists because people are different. However, the difference between these two, where most of the questions will come in, by the way, is that between the group variance, you have treatments because every single group is taking a different treatment. Within the group variance, they're all the same as each other. If you take the first group, they're all taking the same treatment. They look at the second group, they're all taking the same treatments. They look at the third group, they're all taking the same treatments. So it doesn't matter if coffee works or if it doesn't work, they're all still taking the same treatment. This is why here they don't write anything. They don't write anything because even if they wrote something, they're all taking coffee. So if someone took coffee and he got an 8, and someone took coffee and he got a 9, how can you say that coffee is causing the change? No, it's them being different causing the change. That's why within the groups, there's no such thing as treatment causing the change. It's only individual differences and errors of measurement. However, with between the group variance, no, the treatments can cause a difference. Like we saw earlier, coffee was getting people into the 8s and the 9s and the 10s, but people taking water were in the for example 0, 1, and 2. How can you explain that change? Well, it could be individual differences. Sure, that has a role to play. It could be inaccuracies in measurement that also has a role to play. But the major role for causing such a substantial change is probably treatment effects. That's why with between the group variance, we have this added bonus of treatment effects. That's why they say here that the within the group variance is independent. It doesn't care if the person is taking coffee or whatever, because within that group, all of them are taking coffee. If my within the group variance is 2, it doesn't matter if I give that group water or coffee or tea or whatever. It's still going to be 2 because everyone in that group in that group is taking the same intervention or treatment or whatever. However, between the groups, they're taking different treatments. So it depends on whether the null hypothesis is true or the alternate hypothesis is true. Because if the null hypothesis was true, the between the group variance will be low because the treatments are different. The treatments aren't doing anything. So all the groups are sort of similar to each other. But if the alternate hypothesis was true, the null hypothesis was false, then your between the group variance will be high because the treatments are actually making a difference. So what's our null hypothesis? Our null hypothesis is that all of the populations are the same. They all have the same mean. None of them are different from each other. The whatever we're testing doesn't work, yada, yada, yada. Your alternate hypothesis is that at least one of the populations is different from the other. Okay, it's different from the other, either positively or negatively or whatever. So does this independent and dependent make sense to you so far? Okay, I'm seeing some yeses. Yes, perfectly. Okay. Now he says some really important sentences here which build onto that theory that we made so far. If these two numbers are similar, if they're similar, equal in value, then we don't have a reason to reject the null hypothesis. In other words, we must accept the null hypothesis, which makes sense. If these are similar, sorry, let me erase. If these are similar, meaning that this does not work, then we will accept the null hypothesis because your f value will be close to something like 1. And if you put 1 into an Excel sheet to turn it into a p-value, that p-value will be something like 20, 30%. If you have a p-value of 20, 30%, is that considered significant? No, it's not considered significant, right? If you have a p-value more than 20%, what you say is there is no statistical significance and you reject the alternate hypothesis. In other words, you accept, there is no reason to reject, you accept the null hypothesis. Right? So if it's similar, they're similar, you accept the null hypothesis. Or the way he says it is kind of like, he twists it, it's like, there is no reason to reject the null hypothesis, which is the same thing, right? It's the same thing. However, if the between the group variance dominates, if it's a very high number when compared to within the group variance, then the difference between the groups means that it's contributing to the variance. It's contributing to a very large difference between each group. That means that we should reject the null hypothesis. right? So does this make sense? This is incredibly important for theory. This is incredibly important for most of your MCQs. Because really, he might just give you one question. Osama, you said no. Basically, remember when the problem is, I remember you said, yeah, because the drug, for example, is effective. Yes, yes, Lemma, because the drug example is, yeah, Osama said yes, okay. Because look, I'm going to ask you all right now. Between the group variance, I'm gonna keep writing them like this because this is just easier to understand. And within, oh my God, within the group, already butchered it. Okay, if between the group variance is high, okay, you'll get a high number here. Your p-value then will be less than 5%. What do you do? Do you reject the null hypothesis or reject the alternate hypothesis? Which one do you reject? Reject the null hypothesis. You see, this is how he'll give you questions. He'll tell you, for example, between the group variance was increased substantially more than within the group variance. Which of the following actions must be taken? And he'll write for you, reject the null hypothesis, accept the null hypothesis, uh, uh, accept the alternate hypothesis, and then let you pick. And then you have to pick the right answer. So what if this number and the number above it are sort of equal? Then what do you do? Accept the null hypothesis, or if you want to flip it, yeah, not reject null, or if you want to flip it again, reject the alternate hypothesis, the alternate, right? So this is theory. This is the theory of ANOVA. Now let's start with calculations, right? So this is an easy mark, very easy mark. Don't miss it. It's going to be maybe one question in your exam. Don't miss it. If he doesn't bring it, all the better. But if you brought it, you shouldn't be missing this mark. So he'll give you all this. All right, let me just circle all of it. He'll give you all of this, right? And now your job is he'll tell you find f. He won't tell you convert f to p-value. Please don't ask me that. He won't tell you that. The only way you do that is with an Excel sheet, or for example, Jamovi, RStudio, these programs, these biostatistical programs. That's where you do that stuff. Here on paper, you cannot convert f. You can, but this is not the you don't need to know it. Point is, your job is to find f. So now, how do you find f? To give you the grand scheme of things, what is the f? It is between the group. Yeah, it is between the group over within the group. So now, how do we find between the group and how do we find within the group? So let's first focus on between the group variance. Okay, so it's a number of steps. It's a number of steps. The first step is we need to follow this formula. You need to have this memorized by heart. Okay. Now, he also might not give you this. This is something you have to come up with. So what is the grand mean? It's basically you take this mean, you take this mean, you take this mean, and you find the mean of that. That's called your grand mean. Then you find the number of groups and you call that k. You can call whatever you want, but for this example, it's called k, right? Because in the formula we have k. And in this example, we have 3 groups. So k is 3. That makes sense. Number of scores in each group. N equals 9. Now, I always see this problem happening. N is not your number of groups. K is your number of groups. N is something differently entirely. We'll get to it soon. Okay, it helps us find the between the group variance, but we don't use it in the first step. Your first step is using K, which is the number of groups. Your N is the number of people in every single group. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. Right? So you first start using this formula. I know this formula looks very, complex, but it's actually very simple. Basically, you take each group mean, right, and you minus it from the grand mean. Okay, so you take, for example, 6.33 minus 5.33. I think it's best we actually do this. Right. So look, we'll do the first one. So it's 6.3. I wish I had my mouse. Minus 5.33, and then you square this. Oh my God, Osama, I love you, because I was just about to mention this. And then you do divide by k minus 1. So what is k minus 1? It'll end up being 2. So 6.33 minus 5.3, this will be 1. 1 squared. 1 divided by k minus 1 is how much? Is going to be 1 over 2. This entire thing will become half. Do you all agree with me on this, or did I do it too fast? Are you all with me? This is half. Now, this little sigma here, I don't know if it's called sigma. Point is, what this thing says is that you have to do this again for this mean and this mean. So let's do it again. So if we put 4.33 here instead, it'll be -1, but when you square that, that'll be +1 over half. So that'll be another half, right? And then let's do it again for 5.33. If I put 5.33 here instead, it'll be 0. 0 over whatever is going to be 0. So what you do then is when you have these three values, you add them all together. So, half plus 0 is going to be 1. That's where they got this number, right? That's where they got this number. Now, we actually saw this formula during our midterm. This was the formula for variance. Remember, I told you the best way to find variance, how do you do it? You first find the mean, and then you minus each single thing from the mean, and then you square that value at the end and divide it by n-1, depending on how many you have. This is the same exact thing, but instead of taking these values, you're taking this value, and this value. So this step, by far, is nothing new. This step is nothing new. We talked about this in our second or third lecture about variance. Yes, so Shahad got it as well. This is the same as variance from Dr. Hassan's lecture, what I taught to you in the second or third lecture. This is the same exact stuff. It's done in a way that looks very, very confusing and stuff. No. This is the same exact thing. So does this step so far make sense to you? So now what's the next step? It's very simple. We have this 1. What do we do with it? We multiply it by n. And there you go. You're done. You got your between the group variance. Now what is n? N is how many you have in each group. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case, it's 9. Sorry, it's 9. 9 people in each group. Now I know what all of you are going to ask. Yeah, Nida or Nida. Point is, you add all three in the end. Yeah, so here we had half when we did it with 6.33. Here we had half when we did it with 4.33, and here we had 0 when we had with 5.33. And you then at the end you do you add them all together, and in this case, half plus half, you got 1, right? Now this n, you multiply that by this 1, and you'll get your between the group variance. In this case, it was 9 because our n is 9. That's how many we have in each single group. And then we got our final between the group variance of 9, right? Do you all understand how we get between the group variance? It's very simple. You do the variance thing that we already know and understand. It's just a bit more complicated. Yeah, is n the same for all groups? Yeah. So Samiha, with ANOVA, it's highly encouraged that you put the all the groups the same number of people. Now, in reality, sometimes this doesn't happen, but for your exam, he's not going to do this trick. He's going to give you the same number of people in each group. So 9 here, 9 here, 9 here. In reality, it's going to be like maybe 10 here, 9 here, whatever. But yani, he's not going to bring you that thing because he didn't teach it to you. So you're not going to, this is very advanced. You don't need to know. Even I don't even know it. So yani, point is, there is a way to control it, but we don't need to know it. Okay. So now all of us know between the group variance. It's the more complicated stuff. Within the group variance is very simple. He'll give you the variance of this group, the variance of this group, the variance of this group. Just find the mean. Just find the mean. So 10 plus 10 plus 10 divided by 3. That's your within the group variance. So then you do 9 over 10, and you'll get your answer. In this case, it was 0.9. So 0.9, 0.9. So between the group variance is very similar to within the group variance. So what do? Do you reject the null hypothesis, or do you reject the alternate hypothesis? You reject the alternate hypothesis because this will give you a p-value that's very close to or higher than 5%. So you reject the null hypothesis, so on and so forth. Do you all sort of understand this? Let's take another example. So here he changed the means. Look, here the mean is 8.33. I didn't. Okay, Marwan, not the last point. Okay. So the last point basically. Okay. You didn't get the last step? How does the f value tell you it's not significant? Okay. Ghadir, yeah. I know I really went fast on this. I'm assuming that's where I lost all of you. So look, I do not have a software besides Excel sheet that tells me what the f. Look. See, I mentioned this earlier. I told you no one asked me how you turn this number to a p-value. So now I know what you're all asking. You're like, Khalid, how are we supposed to know during the exam? He's not going to ask you that. He's going to ask you, calculate F. He won't tell you what do you do then later with F. But I'm telling you right now, practically what you should do. You put this 0.9 into an Excel sheet. The Excel sheet will take it and tell you, okay, this is 30% p-value. Then you interpret it, okay? So he might give you a little trick. He'll tell you an F value came, which was like 0.9. This corresponds to a p-value of 20%. What does this p-value? What is the next step? And then he has choices like reject the null hypothesis, accept the alternate hypothesis, so on and so forth. Then you pick. So I can know if it's significant or not. Yeah, if you only have the F value, you can't know. You can't know, right? You can't, right? Reject the alternate. Look. I need to really make this clear. If the F value was like 10, you don't need Excel sheet. That's very easy. خلاص. 10 means like it's 100% significant. P-value is going to be like 0.000000005. Okay, Marwan. Look, guys, stop asking questions. Relax for a second. Relax, because I know what you're all asking about. Okay. There is a specific value for the F that is the cutoff. Dr. Hassan doesn't want you guys memorizing that cutoff. He doesn't, like, there's no point in memorizing that cutoff because no one memorizes that cutoff. People only memorize the p-value being 5%. That's the one they memorize. That's only the one they memorize. So during the exam, he will just tell you what is the F value, calculate it. However, he might tell you that, hey, we got this F value, which gave us a p-value of 2%. What is the what is the step that we need to do now? And the answer should be rejecting the null hypothesis and accepting the alternate hypothesis. I'm not saying anything new. This was everything that we talked about yesterday and the day before. The idea that you're all confusing with is that, Khalid, how did you know that F value is 0.9? It tells you that the p-value is, I'm just كذا, I know because I know that 0.9 because I know that oh my god, because look, because I'm following this. Like, this is how I know, because if the between the group, if this number and this number are similar, then most likely the alternate hypothesis will be wrong and the null hypothesis will be correct. I'm just following this rule, which is a very simple rule. It doesn't have anything to do with numbers, right? If your F value is like 5 is huge. Like the cutoff I remember for the F value is like 2.33, but I don't know if that's correct or not. I'm not sure, but I don't use that cutoff. I just know, okay, it's a number around 2. So if I got an F value of 1,000,000, I know it's going to be significant, right? I don't need Excel sheet to tell me that it's going to be significant. If I got an F value of like 5, 6, 7, I know it's significant. I don't need Excel sheet. The problem is if Excel sheet is like, okay, if the F value was like 2.5, I'm not sure if that's going to be significant or not. I put it into Excel sheet. So stop asking how you turn F value to P value. I'm just giving you a quick idea that, oh, hey, this number is really high when compared to the 10. Therefore, this number would be very high. Therefore, you reject the null hypothesis. I'm just following the same exact rule that I mentioned here for you guys. The same exact rule. Nothing's different. Nothing's different. So do you guys understand this? Yeah, I know one. You got it. Okay, and everyone's getting it. Okay. So now let's do the same exact example, but with different numbers. So this is the same example, just different numbers. Let me erase all the ink. Okay, so we're gonna do the same thing. Our grand mean, you take this mean and this mean and this mean, you divide them by 3, you add them together, you divide them by 3, you got this grand mean, right? It's 5.67. Okay. Number of groups, we have 3, so our k is 3, right? The number of people in each group, it's also 9. I'm not gonna count it. It's 9. It's basically 9. So n equal 9. Our sampling variance is going to be the group mean. So let's do this. 8.33 minus 5.67, right? And then you square all that, and then you divide it by k minus 1, which is 3 minus 1, which is going to be eventually 2. Let's actually do this because I want to see what it's going to be. So 8.33 minus 5.67. So I got this value, 2.66, and then I'm gonna you can square it, but you have to like use your this. Okay, where's the hell the square? So I got 7.07. I'm going to divide by 2. So that's the first value that I got. I think this is the value everyone got, 3.5378. And then you'll probably get the same value with this one, the 3.33, since it's similar to the 8.33, just negative. So I'm gonna do times. Actually, point is, you're gonna get a value very close to this. I'm too lazy to do the actual calculation, but yeah, you're gonna get a value very close to that, and that's gonna be your answer, right? 0.67, 2.66. Let me just make sure. 3.33 minus 5.67. Yeah, 2.33 and 2.34. So very close, very close. And then you have 5.33 minus 5.67. Yeah, I'm sure if you do it, it's gonna be very close to this value, right? So let's say you did that step without any calculation mistakes, and you got 6.33. Now, what's the next step? Is that your between the group variance? No. You multiply that by n, and that answer will be your between the group variance. In this case, they multiplied it by 9, so 9 times this, you'll get 57, and then that'll be your between the group variance. What about your within the group variance? It's going to be 10, 10, and 10. That's going to be 30. You add them all together, then divide them by 3. You're going to get divided by 3, then you're going to get 10. And then this is your between the group variance. This is your within the group variance. You're going to get an answer of 5.7. And you answer that during the exam, 5.7. Okay? So do you all understand the calculation side of it? Is someone, yeah. No, we do not. Look, here, the F value is really high. You reject the null hypothesis, right? Because if you put this number into an Excel sheet, he doesn't put this in the slides, but if you put this number into an Excel sheet, this will give you a p-value less than 5%. So you reject the null hypothesis. Do you understand this point? Do you understand this part? Yes, I know it's confusing because he's not telling you how to convert F to p-value, but this problem will not happen in the exam, right? He might give you the results and then give you the p-value along with them. Don't use the F value, use the p-value to make your decision, right? So that is ANOVA. That is ANOVA. We're done with ANOVA. Now it's just a bit more theory on ANOVA. So we all understand between the group variance. We all understand within the group variance. We know how to calculate. We understand that the between the group variance is dependent because it's affected by the null or alternate hypothesis being true. And we know that the within the group variance is independent. We know that if these numbers are similar, then we accept the null hypothesis. We know if these numbers are different, specifically if the between the group variance is higher than the within the group variance and higher by a lot, then you're going to basically reject the null hypothesis and accept the alternate hypothesis. This is the revision. I did not say anything new. Can we do another example if there's time at the end? Yes, of course we can do an example at the end. But I don't think there is enough time at the end because we have 15 minutes left. Okay. So here they give you another example. So you were accepting and rejecting. Which one? I was accepting and rejecting which one? Based on last rule. Yeah. Based on this, I'm accepting and rejecting. Yeah. So here I saw that they're very similar to each other. I was like, oh yeah, no hypothesis is true. Here I saw that this is very high, higher than the 10. So I'm saying, oh, okay, so alternate hypothesis. And he even agrees with this. Like the answer is right here in front of you guys. I just noticed it, but it's right here. So look, in this example, the null hypothesis is true. In this example, the alternate hypothesis is true. So yeah. Now he's giving you another example. And basically this combines everything that we learned in the previous lectures. This is why I keep, telling you to always ask questions so that we can all understand what's going on. So here he gives you an example of how we're going to use ANOVA. He says that we have one group that's taking no therapy, placebo, conventional therapy, and new age therapy. This is an example of Parkinson. Now this is really important. If you do ANOVA on all of these, I'm going to circle all of them. If you do ANOVA on all of these, and if your F value tells you it's significant, this is really important. The only thing that you can know is that one of these therapies, one of them, only one of them or more, at least, sorry, that's the word I want to look for. At least one of them, when compared to another treatment, is significant. So that's important. Now, or that no therapy does not work, or that your sentence is kind of like double negative. So I don't really know how to comment on that. But like the idea is that if it was significant, basically you see we can look. Let me show you how crazy it is. We can compare no therapy to placebo. We can compare no therapy to conventional. We can compare no therapy to new age. We can compare placebo to conventional. We can compare placebo to new age. We can compare conventional therapy to new age. And the other ones are opposite, so it's fine. We covered everything, right? All of those comparisons, if the F value was significant, the first step, ANOVA, was significant, the only thing that you get as a researcher is that at least one of these many different comparisons is significant, right? So you can already see the problem. How can we know which one? How can we know which one? So this is the step beyond the F value. So how do we know? So for example, here we can compare group 1 to group 2, group 1 to group 3, and group 3 to group 2. Those are all the different comparisons, right? There's nothing else that you can make. Now, here our F value is significant. So how do we know which one is the actual significant one? It could be this one that's the only one that's significant. It could be all of them that are all significant. But how do we know? There are extra steps beyond that. So what are the steps? Okay, he puts in some assumptions. We'll go back to it. Basically, he's telling you to use Jamovi because Jamovi is amazing. The idea, I'm gonna skip ahead, then I'm gonna show you what's important, then we're gonna go back over the slides. The last slide is what's important. This is your summary slide. There are 2 steps that you can do when you do ANOVA. You see, let me go back to this example. Here. This is good. Now, before we start the study, we can outline what we're interested in. This is called a priori. This means that, hey, before I start the study, I made my groups. I have no therapy, placebo, I have a conventional, and I have like new age therapy, right? A priori means that before I collect the data, before I do anything, I am going to outline what I want to compare. So for example, I want to compare no therapy to placebo. I think that will be very interesting. I want to compare placebo to conventional, and I want to compare placebo to new age therapy. Okay? All the other comparisons, I don't care about them. This is called priori. When before you collect the data, you make your bets on what you actually want to see. So although there are more comparisons that could be significant, I don't care about them. This is called priori. Now, priori in general is frowned upon because priori, I'm being biased. Why am I picking these 3? I have no evidence to suggest that I'm picking these 3 because they might be relevant. I'm completely biased in it. That's why priori is generally not advised. Okay, simple. Now, the other technique is called post hoc. Post hoc means post collection of the data, post analyzing the data. You got your F value. Now you pick which ones you want to see based on your data. So for example, here would be me doing post hoc. Oh, hey, look, placebo got very low marks. Or sorry, no therapy got very low marks. Placebo got very good marks. I think this would be an interesting analysis. I know there's something significant in here, but I'm only picking it after I see the results. This way, I'm not biased. I'm actually seeing the results in front of me. I'm not saying, oh, this will be interesting because I think it's interesting. No, this might be interesting because, hey, look at the values here and look at the values here. Let's do a test after here to see this one. This is called post hoc. Okay. So do you all understand the difference between priori and post hoc? Priori is generally frowned upon. Post hoc is the way to go. So now this last slide will be very simple. Okay, so with a priori, the only test you can do is called a Fisher's LSD, least significant difference. Basically, the only thing you need to know about it is that it's a setting in Jamovi, which will find to you which ones were the significant ones. It will run the best way I like to explain it is that it will run t-tests among all the different 2 different comparisons. So between this one and this one, it will run a t-test. This one and this one, it will run a t-test. This one and this one, it will run a t-test. Right? So this is a good way to do it. This is one way to do it, I guess. Okay, priori, Fisher's LSD. Just memorize those. Priori, Fisher's LSD. It will try and find significant values between the comparisons we picked. Post hoc, it's more interesting. And it has a lot more options because most people use post hoc. Therefore, it's more flexible. Okay. If there are, three conditions. Okay. Forget the term here, three conditions. Just change conditions to groups. Sometimes biostatisticians call conditions as groups. If you have three conditions, you use something called the protected Fisher's LSD. The reason they call it protected is because you've already seen the results, therefore you are protected. You know there's a significance somewhere, and you're trying to go for it. Compare that with a priori, you only use a Fisher's LSD. You don't use a protected one because before you start, you don't know if there's a significance, right? But the reason here it's protected when it's post hoc is because this Fisher's we already did our F value and we know that there's one significance. We look at the data and we say, hey, this might be interesting. At that point, your Fisher's LSD is called the protected Fisher's LSD. Okay? And it's the same thing. Think of it as running t-tests between the two comparisons that you picked after you saw the data. However, if you have more than three, you use Tukey or Bonferroni. Memorize that. I'll explain in a second why that is, what Tukey and Bonferroni do, and why you use it when it's more than three, or more than three groups, like 4, 5, 6, 7. If you had more than 6, you use something called Benjamin Hochberg. Okay. Now, why is this the case? Why don't we just do Fisher's? Why do we have Benjamin Hochberg, and why do we have Tukey and Bonferroni? Well, it's very simple. This ties in with every single thing we learned, okay? This ties in with everything. Remember when I told you back in the confidence interval lecture, that was a long time ago, right? Like, oh, I told you that if you have 20 studies, and let's imagine that the reality is that the null hypothesis is true. On average, one of those studies will not suggest that the null hypothesis is true. It will we will reject the null hypothesis. So why does this happen? Because it is possible that as you keep repeating and doing more and more tests, you have a chance to get an alpha error. Does this make sense with all of you, or am I losing some people? Yes, 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 yes. You see how everything is starting to link with each other. So now we have a problem with ANOVA. If I have too many comparisons that I want to do, how do I know that it's actually significant or if it's an alpha error? This is a problem. Therefore, for that reason, Fisher's, if you ever use Fisher's, you have to limit to only 3 comparisons. Only 3 comparisons. Don't go more than that, because when you go more than that, basically, I'm going to show you this beautiful thing here. If you have, for example, only 3 groups, there are only 3 comparisons you can possibly do. If you have 4 groups like we just saw, there are 6 comparisons. So you can only pick 3 of those comparisons that are interesting. That example with the placebo and the conventional therapy and the 4 different groups, there are 6 total different comparisons. If we want to use Fisher's, we're advised to only use 3 comparisons, because if we go more than that, then we might get an alpha error. Our chance of getting an alpha error is quite high. So we might think that, for example, let's say we did all of them. Let's say we did all of them. Okay, all of them. And the only one that really is significant, let's say, for example, it's placebo to no therapy and placebo to conventional. Those are the only 2 that are significant. If we did Fisher's for all of them, maybe we find that, new age and conventional are now significant. Now we don't know, is it really significant? Or is that an alpha error? For that reason, whenever you do Fisher's LSD, 3 comparisons only. You can't go more than that. Even if you have 10 million groups, pick 3 comparisons. That's it. All right? You all understand this. Now, he gives you, now let's continue the slide. So he gives you some assumptions, all the participants selected at random, and then it will be accurate. Yeah. If you pick 3 comparisons, you can trust whatever significance it comes. It could still be alpha, but the chance of getting alpha with picking 3 comparisons is less than the chance of picking 4 comparisons. So that's the whole idea. 3 is fine, but an alpha level being higher than that is terrible, right? So that's the idea. With even if you just pick 1 comparison, there is a 5% chance of getting an alpha error. That's always there. But the more times you keep doing it, that alpha error goes up and up and up and up and up and up, right? It keeps going higher and higher and higher and higher because you keep repeating the study. at some point you're actually going to, this is an important thing that I brought up. It's kind of a little, it's more of a puzzle than a thing. But yani, the idea is that when I just said that your alpha error increases, it doesn't actually increase. It's always 5%. But if I told you what's the chance of you making an alpha error with 20 different studies, like 20 different comparisons, it's not 5%. It's more than that because you only need one alpha across all those studies. So the chance actually increases. I hope none of you got confused by that, okay? The entire idea is that the more times you do a study, you have a higher chance of getting that alpha. Not because alpha is higher, but because you keep repeating the study, okay? The data in the group is normally distributed. The variances are equal, but not necessarily. What is this? But not necessary if, yeah. So this is just, this is a random fact you need to know. Just memorize. These are assumptions that are usually everywhere. Oh, they have to be random. They have to have equal variances. They have to have normal distribution. But just know this, that if the variances were not equal, just use Welch analysis. Just memorize that, just for the sake of your exam. Okay. There's no real understanding behind it. He tells you this is how you can use Jamovi, yada, yada, yada. We don't care about this. Jamovi stuff, we don't care about this. Confidence intervals. So we can use the confidence intervals actually to make our decisions. So look, notice how the no therapy does not cross the placebo. So this and this are significant. And, doing this is terrible because you don't know that now making all these comparisons, you don't know if one is significant just because of it being significant, right? You don't know, because here what we're doing is we're actually comparing all of them with each other. We're actually doing all 6 comparisons right now. And I think he talked about this during your lecture. He told you, wow, look, this is significant, this is significant, this is significant, and this is significant to this, and this is significant to this. Wow, so much significance. Well, guess what? Maybe one of those was an alpha error. Maybe none of them were an alpha error. But because we did so many comparisons, it's possible that one of them was an alpha error. It's much more likely that one of them is an alpha error since we're doing a lot of comparisons. But here he gives you the F value. Look at this. The F value was 18 and he got a P value of like less than 0.00001. So yeah, this means that there is one significance or more. We don't know how many, but there's at least one significance. So then he fishes for it. He uses Fisher's LSD or whatever. Like from then on, it depends on how many comparisons you want to do and so on. Okay. But the general idea is that you have groups. You get your F value. Your F value is a specific number. Yada yada yada. You turn it into a P value. Your P value tells you all their significance. Then you understand. Okay. So one comparison between the groups or more is significant. Now I need to make a choice. Do I pick Fisher's? Do I pick Bonferroni? Do I pick this? Do I pick that? Blah 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 blah. Effect size, he talks about this. This is lab stuff. It doesn't matter. If you, in case you want to know, all you do is you multiply this number with this number, you'll get this value. Then you multiply this number with this number, you'll get this value. This is lab stuff. You have to use Jamovi, right? And then you put this number over the addition of both. So he gets like, or sorry, this number over the addition of both. So it's 6481 over the addition of both. You get this value, and generally an effect size more than 30% is a very good effect size. So in this case, it's 62%, very good effect size, which it's pretty good. But yeah, and remember, if you remember the lecture about confidence intervals that we did yesterday, this was actually one of the nomenclature of effect size. It's theta squared or eta squared. Okay, then he reports the results. He tells you the means, yada, 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 yada. And he intentionally gives you all of them and intentionally shows you the p-value so that you can make your decision. What does this p-value mean? It means that there is at least, you see, there was a highly significant difference between 2 or more treatment means. That's all you can understand from this p-value. Then he gives you the confidence intervals, yada, 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 blah, 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 blah. So then he says, why do we need multiple comparisons? Because the significant F only tells us that there's one or more comparisons that are significant. We have to fish for them. We need to know which means are different from which other means. So then we do multiple comparisons after it. This is everything that we talked about. Either you do it before you actually collect the data or after. Generally, this is 100% frowned upon because your turn. How on earth do you know that placebo and this would be interesting without any data collected? It's very biased. So that's why they think priori is frowned upon. That's why no one likes priori. So then here he's doing, yeah, he's saying which ones would you consider priori. So he's basically saying which ones would you consider subjective and which ones objective. So subjective ones would be maybe no therapy and placebo. That looks interesting, but a post hoc would only be after you collect the data. Here he's showing you how when you have more groups, you get more comparisons, right? This is only if you want to compare every single group to the other. So if you have just 12 groups, you get 66 comparisons. You have to pick 3 out of all those 66 if you're using Fishers. Imagine that. So how are you going to make that decision? It's very difficult to come up with that decision. So here we don't really call it alpha error. I kept calling it that, but that's not exactly what it's called. It is alpha error, but he gives it another name. It's called family-wise error rates. The chances of finding something that's significant when it's not significant. It's the same exact thing as alpha. It's just a different name. It's called family-wise error rate, and it gives you this meme. It's very funny because it gives you the actual idea. So here they're saying jelly beans cause acne, investigate, but we're playing Minecraft. Jelly beans cause acne. They didn't find any relationships, so the p-value was more than 0.05. I hear that a certain color causes it. So guess what? They check every single color, and this one was not significant. This one was not significant. Not significant. P-value more than 5%, more than 5%, more than 5, blah 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 blah. And then hey, look at this. This one happened to be significant. Do you guys think that? Wait, of course, it's possible that green jelly beans could cause acne, but do you guys think that this was an actual significance? Do you guys think that green jelly beans cause acne? No, it's probably a family-wise error rate. Of course, okay, this is an important question. Is it possible that green jelly beans can cause acne? Is it possible? Yeah, it's always possible. It's always possible. But in this case, it looks so obvious that it's probably not. It's just because they keep repeating the study. And then, hey, they found that the green jelly beans were the ones causing it. So then they published it, and that makes absolutely no sense, right? It doesn't make any sense. He's just highlighting to you how the family-wise error rates can happen. Okay, so post-hoc tests, how did they arise? Sometimes the hypothesis, blah, 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 blah. So now we're going to talk about the other ones, Bonferroni and all that. This is Fisher's. Fisher's is basically just doing a protected t-test. This is how people explain a protected t-test, called protected because you already know that there is a significance. There's no way you can be wrong. You know, you can only be wrong if you have 6 comparisons and you only have to pick 3. You might miss the one that's significant. But the entire idea is that you're protected because, hey, you know there's a significance somewhere here, but you don't know which one. You got to fish for it. So that's why they call it Fisher's. But yeah, it's usually the most powerful test, meaning that if there was a difference, this Fisher's test will detect it. Power is usually over 80%. That's why people love it. So since it's the most powerful, people give it the name of the most liberal. It's not really conservative. It's just more liberal. You know, it's more powerful. Okay, now Tucky. Now Tucky, all you need to know about it, it's not explained how, but if you have more than 3 groups, if you have more than 3 comparisons, more than 3 comparisons, then you use Tuckies. You use Tuckies because it controls family-wise error rates, right? It's the best one that controls family-wise error rates, right? Look, apart from Fisher's, it is the most powerful. When do you use it? When you have more than 3 comparisons, usually when you have more than 3 groups, because you're going to have more than 3 comparisons when you have more than 3 groups. But Bonferroni is a good alternative to Tucky, right? It's not better than Tucky. Tucky's always better, but Bonferroni is a good alternative in case you cannot use Tucky. So how does Bonferroni correct it? How does Bonferroni control family-wise error rate? You have to know this. Basically, imagine you have 5 comparisons. You would divide alpha by 5. If you have 10 comparisons, you divide alpha by 10. Therefore, as you make more comparisons, didn't I tell you that your chance of getting an alpha increases? So how do you compensate this? Your alpha actually decreases. By alpha, I mean 5%. Yeah, so alpha, which is 5%, it decreases the more comparisons you have to do. And this makes sense because as you have like 6, if you have like 10 comparisons, you might get an alpha error. So how does Bonferroni correct for it? It divides alpha by the number of tests you're going to do. So if you have 10 comparisons that you're going to do, it divides alpha by 10. So you're going to have alpha become, for example, 0.05, which is like 0.005, which is like, I don't know, like 0.05%. Imagine an alpha of 0.05%. Yeah, increased comparisons decrease the alpha, right? So that's how Bonferroni, but he might tell you, would you want to use Tucky's or Bonferroni? Tucky is always the answer. Tucky is the one that is better, right? But Bonferroni, He's not going to ask you how does Tucky's control family-wise error rate. It's not mentioned in the slides. But for Bonferroni, it is mentioned. You have to know that with Bonferroni, it divides it by the number of tests you do. With that said, he gives you some Jamovi, he gives you more Jamovi. This is an example of Fishers, yada, yada, yada. This is just lab stuff, more lab stuff, more lab stuff, more lab stuff, yada, yada, yada. He gives you a way to summarize everything. He gives you priori and post hoc. This is a beautiful summary. For Benjamin Hochberg, he doesn't really talk about it much. He just says that if you have more than 6 comparisons, you use Benjamin Hochberg, right? Memorize that. There's nothing here that says how Benjamin Hochberg controls it. No, nothing like that. This is I'm sorry to say it. This is the one time I will say it to you guys. You have to memorize these. Just memorize them, and I'll give you a quick summary behind them. Fishers, 3 comparisons. What is it? It's like t-tests between the comparisons that you find interesting. Could be priori or could be post hoc. With post hoc, if you choose it, it's called protected Fishers LSD. Protected because you know that there's significance and you have to fish for it. With post hoc, you have other options. For example, you have Tucky. It's the strongest one aside from Fishers. Or you have Bonferroni. Bonferroni is a little bit weaker than Tucky's, but you can use it, and you have to know how it controls family-wise error rate. It does it by dividing the alpha by the number of comparisons you're going to do. If you have more than 6 comparisons, you go from Benjamin Hochberg, and that is ANOVA. I know the last part is really a lot of memorization, but there's no real understanding. This is not the point where you understand all the detail about these tests because it's way too much. So with that said, we have finished ANOVA. I don't think we have time for another example of this because I think everyone wants to start, and I think we all should pray Isha. But just really quickly, like 10 minutes, if you guys have any questions from anywhere, go ahead and ask. Okay? You're all welcome. So I always no. I did not say you always choose Tucky if you have. Look. If he tells you, for example, you need to pick more than five comparisons, which of the following is the best choice, and just leaves it like that. He doesn't tell you anything else. You pick Tucky. Yes, Tucky. All right. I'm really happy that all of you know this. I'm kind of sad that it's only 30 participants, but I'm sure everyone's gonna hopefully watch these videos. So for priority Fisher, is it always for 2 groups? No. Remember, wait a minute. Yeah. Fishers, the actual Fishers test is always between 2 comparisons, like, one comparison between 2 groups. So, like for example, let me show you how it's actually done. Like, you would do a Fisher's test between, for example, no therapy and placebo. What's the best way to understand and memorize the null hypothesis? Watch my videos on the null hypothesis. Watch my videos on yesterday's. I know you were there, Osama. Watch my videos again.